Dear students, I welcome you back to the Advanced Mathematics 2. This is the third session of inverse Laplace transform. From the last two sessions, we have started the inverse Laplace transforms and their examples. In particular, in the last session, we started the problems on using the partial fractions. In the partial fractions, mainly we discussed about the expressions of these types. In the denominator, there are linear factors x plus a, x plus b. They are non-repeated linear factors in the denominators. In that case, we used the partial fractions of the form a divided by one linear factor plus b divided by another linear factor. Similar way, the denominator has the repeated linear factors. So, x minus a is repeated 3 times, raised to 3 means. So, in that case, we use the partial fraction of the form a divided by x plus a, b divided by x plus a whole square plus c divided by x plus a whole cube. So, in this way, we had written the partial fractions. And if the denominator is a quadratic form, fx divided by x square plus 5x plus 1 is a quadratic term in the denominator, another term is linear. In such cases, we used the c divided by 3x plus 4, that is a linear factor. So, wherever quadratic factor is there, we used ax plus b divided by x square plus 5x plus 1. Here, the quadratic term which cannot be factorized. When this quadratic factor is not able to factorize into linear factors, in that case, we use the form ax plus b divided by x square plus 5x plus 1. So, we solved one example in earlier. Now, we continue the problems on using partial fractions. There is an example. Find L inverse of 3s plus 6 divided by s into s plus 3. So, it is a problem using a partial fraction. See the denominator term here. It is a proper fraction. Numerator polynomial degree is 1 and denominator polynomial of degree is 2. So, it is a proper fraction. So, see the denominator, there are real and non-repeated factors. So, s minus 0 is one factor, s plus 3 is another factor. Both are linear and non-repeated. So, as per the table specification, so split up the into partial fractions. How it is done here? 3s plus 6 divided by s into s plus 6. So, that can be written into a partial fractions a divided by one linear factor s plus b divided by another linear factor s plus 3. So, here the problem is to calculate the values of a and b. So, for that multiply both the sides of the equation by this term, denominator term s into s plus 3. So, by multiplying that, we get that term cancels on the left hand side. The remaining is 3s plus 6 is equal to a into multiply s into s plus 3. So, that s cancels a into s plus 3 plus b into s plus 3 divided by s plus 3 is there. So, s plus 3 cancels, it is b into s. Then simplifying this, multiplying s plus 3 by a into s, as plus 3 into a, 3a plus b into s, bs. Now, to find the values of a and b, we make equating the coefficients of left hand side to the right hand side. So, I have clubbed the coefficient of s here, a into s, another term is b into s. So, it is written a plus b into s. So, the coefficient of s is a plus b. The remaining is a constant term 3 into a as it is. Now, equating the coefficients of like powers of s on both sides. Consider the coefficient of s on both sides. Say the left hand side, the coefficient of s is 3. So, 3 is equal to the right hand side, what is the coefficient of s? A plus b. So, that we get one equation a plus b is equal to 3. Similar way, I am equating the constant terms on both sides. Left hand side 6 is the constant term, right hand side 3a is a constant term. So, 3a is equal to 6. So, using these two equations, you find out the values of A and B. It is clear from the equation 3A is equal to 6. So, A becomes 2 here. A is equal to 2. Substituting the value of A in the first equation, A is equal to 2. So, B is equal to 3 minus 2, it is 1. So, that the values calculated are A is equal to 2 and B is equal to 1. Now, substituting back in the equation here. So, that is equal to L inverse of A divided by S. A means 2 here, 2 divided by S, plus L inverse of B. B is 1. So, 1 divided by S plus 3. Now, using the table of inverse transforms. So, 2 is a constant here. L inverse of 1 by S, we know that its transform is 1. So, 2 into 1 it is. It is a plus term. It is a plus term. So, L inverse of 1 upon S plus 3. What is the inverse of this? It is again the standard inverse Laplace transform table. So, it is by using the shifting theorem, first shifting theorem. If it is only 1 upon S, it is 1. Inverse of 1 by S is 1. So, S is shifted here, S plus 3 means S equal to S is shifted by S plus 3 means A is equal to minus 3 here. So, it is of the form 1 divided by S minus A means e raised to at. So, A is minus 3. So, it is e raised to minus 3t. So, this is the middle term is plus. So, the final inverse of this problem is 2 plus e raised to minus 3t. Consider another example here. See the denominator term S into S plus 1 whole square. Here one of the linear factor is repeated here. S plus 1 is repeated 2 times. So, the factors in the denominators are real, both are real. One factor is S minus 0, another one is S plus 1. So, repeated linear factor is S plus 1. So, as per the rule, for repeated linear factor, the partial fractions are written. For non-repeated, first you write A divided by S, it is non-repeated factor. Next, for repeated linear factors, S plus 1 and S plus 1 whole square. So, B divided by S plus 1 plus C divided by S plus 1 whole square. So, in this way, the terms are written into partial fractions. Now, the problem is to find the values of A, B, C. For that, we multiply both the sides by the denominator term S into S plus 1 whole square. By doing that, we get the left hand side S square plus 1, this denominator term cancels, is equal to A into S cancels, S plus 1 whole square, plus B into here S plus 1 term cancels here, in this S into S plus 1 whole square, in that S plus 1 cancels. So, B into S plus 1 plus C into here S plus 1 whole square, that entire term cancels, only it is S. So, C into S. So, this equation is reduced to this way. Now, simplifying this right hand side, S plus 1 whole square you simplify, A into S square 2S plus 1, it is A plus B whole square type, plus multiply Bs into this bracket, Bs into S, Bs square, Bs into 1, Bs plus Cs. Now, collect the various powers of S and its coefficients. First, collecting the S square coefficients. S square coefficients here, A into S square is one term, B into S square is another term. So, A plus B S square it is. Next, collecting the coefficients of S. So, here one term 2A into S, one term is 2A into S, another term is B into S. So, B is written, another one is C. Totally 2A plus B plus C into S. So, these three terms are coefficient of S. Then the constant term is 1 here, A into 1, there is only one term, constant term. So, after separating the coefficients of various powers of S, now it is easy to find out the coefficients A, B, C. Equating the coefficients of like powers of S. First, I equate the coefficient of S square on both sides. So, left hand side, the S square coefficient is 1 here, 1 into S square. So, 1 is equal to the right hand side A plus B. So, we get an equation A plus B is equal to 1. Similarly, I am equating the coefficient of S on both sides. So, left hand side there is no s term here, you see here there is no s term. So, that the coefficient is 0. Right hand side 2a plus b plus c that is equal to 0 is another equations. Lastly, I compare the constant terms. The left hand side is 1 constant term, right hand side is a. So, that a is equal to 1. So, solving these three equations, find out a, b, c values. So, once we know a values here, a value is substituted in the first equation. So, 1 plus b is equal to 1. So, b becomes 1 minus 1 0. So, a is 1, b is 0. Substituting a, b values in second equation, a is 1, b is 0 means 2 plus c equal to 0, c is equal to minus 2. So, in this way all the values are calculated. Now, substituting back in the partial fractions. So, a value is 1. So, it is L inverse of 1 divided by s. So, b value is 0, you neglect the second term. Coming to c value is minus 2, it is taken constant outside. So, it is remaining is 1 divided by s plus 1 whole square. So, once it is written in the known form, known means these values are known in the inverse table of transforms. So, 1 by s inverse is 1 and this is L inverse of 1 divided by s plus 1 whole square, again by first shifting theorem. If s is replaced by s plus 1, you remove s plus 1, what happens? 1 divided by s square. So, L inverse of 1 upon s square is t, L inverse of 1 by s square is t. So, because of s is replaced by s plus 1, so e raised to minus t. So, a value is minus 1, s is replaced by s minus a is minus 1 here. So, its final inverse transform is 2 into t into e raised to minus t. So, in this way the repeated linear factors, their partial fractions are obtained. See another example here, a linear non-repeated and one quadratic is there. Linear term is s minus 2, the quadratic term is s square plus 1. So, you know how to write the into partial fractions. The factors in the denominators, one is real, other one is quadratic, both are non-repeated here. For that the form is a divided by the linear s minus 2. For quadratic, this is the way of writing b into s plus c, b into s plus c divided by s square plus 1. Then the rest of the work is same, multiplying both sides by the denominator s minus 2 into s square plus 1. So, we get on the left hand side those two terms cancels by multiplying this term. 1 is equal to a into s minus 2 get cancelled, it is s square plus 1 plus bs plus c is another term is multiplied by this. So, s square plus 1 cancels, remaining is s minus 2. Now, simplifying on the right hand side, a into s square, a into 1 plus bs into s, bs square, then c into s, cs, bs into minus 2, it is minus 2 into bs, lastly c into minus 2, it is minus 2c. Then collect the coefficients of various powers of s. So, first consider s square terms here, a into s square, b into s square, there are two terms, combining them a plus b into s square. Then look into the s terms, c into s is one term, minus 2b into s is another term, combining these two, minus 2b plus c into bracket s. And see the constant terms available here. Constant terms are a is one term, minus 2 into c is another term. So, combining them, so we have categorized into the coefficient of s square, coefficient of s and the constant term. So, after doing this, now equating the coefficients of like powers of s on both sides. Like means comparing s square coefficients both left hand side and right hand side. So, in the left hand side there is only single term 1, there is no s square term and no s term. So, for that the coefficient of s square is 0, the right hand side a plus b is equal to 0, this is one equation. Similarly, comparing the coefficients of s on both the sides, again the s term is absent here. So, 0 is equal to minus 2b plus c, that is c minus 2b equal to 0. Now, there is a constant term on the left hand side, that is 1. So, 1 is equal to the right hand side constant is a minus 2c. So, solving these three equations, solving these three equations, substituting into one another equation, we find a is equal to 1 by 5, b equal to minus 1 by 5. So, adding these two, you will get 0 and c is minus 2 by 5. So, substituting these values into the partial fractions. So, a value is 1 upon 5. So, 1 upon 5 that is taken outside because it is a constant. So, L inverse of 1 divided by s minus 2. Next, b is minus 1 upon 5 into s. So, minus 1 upon 5 is taken, s divided by, so we have split it into two terms here, bs divided by this and c divided by this. So, s divided by s square plus 1. Next, c value is minus 2 by 5, then L inverse of remaining 1 divided by s square plus 1. So, we have written into a convenient known inverse transforms. So, all the three are known in the table of inverse Laplace transform. The first one is direct, it is exponential term, 1 upon s minus a, inverse of that is e raised to a t. So, it is e raised to 2t, a value is 2, e raised to 2t. This is compared with the standard Laplace transform of cos t, that is s divided by s square plus 1. So, inverse of that is cos t. This one is again one more standard result, Laplace transform of sin t, it is 1 divided by s square plus 1. So, it is sin t. So, 1 by 5 is common throughout three equations, it is taken outside, 1 by 5 into e raised to 2t, here minus cos t, it is minus 2 times sin t. So, in this way the one is linear and other one is quadratic, the partial fraction forms are referred here. See one of the example, denominator is a quadratic s square minus s minus 2, s square minus s minus 2. So, if possible you try to express into linear factors, So, it is, we can write s minus 2 into s plus 1, if you multiply these two is exactly s square minus s minus 2. So, then once you are able to factorize the quadratic into linear terms, so the as usual procedure, a upon this, b upon this, finding the a, b values using the same procedure, you will get the inverse. The another thing is, the same problem can be solved using the completing square method. Completing square means every quadratic in the denominator we can use the complete square method. Complete square method we studied in the last session. So, we can do any quadratic in the denominator using the complete square method, that I can show you the same problem. L inverse of 4s minus 5 divided by s square minus s minus 2. The usual way, whenever the linear factors are available, we factor into linear factors. Once linear factors are available, you go for partial fraction method, a divided by and b divided by. The another way, we can always have the complete square method, completing square method. Completing square method is, so denominator using the first two terms of the quadratic expression, you make it a square term. So, this formula you can refer, any quadratic x square plus k into s plus c, k and c are the constants. If this is a quadratic term, we can use the formula s k by 2 whole square minus k square by 4. So, you refer for any problem, if you have the quadratic factor in the denominator, whether the linear factors may be available or may not be available, always you can try for completing square method. So, using this problem, s square minus s minus 2, here k value is minus 1, here for that it is 1 s, it is s square minus k value is minus 1, one can write k by 2 is s minus half whole square plus minus k square by 4. K is minus 1 here. K square means 1 divided by 4. If we simplify this exactly again, s square minus s minus 2. Squaring this, s square plus 1 by 4 minus 1 by 4 cancels. Then 2 times of minus 2 times of s into 1 by 2, it is minus s. This minus 2 as it is. For these two terms, this is added here. So, last two terms you simplify, it is s minus 1 by 2 square, adding these two, minus 8 minus 1 minus 9 by 4. One can use s minus 1 by 2 square minus 3 by 4 we can write, 9 by 4 we can write 3 by 2 whole square. So, every quadratic term in the denominator we can use the complete square method, or the linear factors are available, you go for partial fractions. When linear factors are not available or available, always you can go for completing square method. Now, use the shifting theorem and calculate the inverse. See another example here. Numerator is a linear, denominator one linear factor, other one quadratic factor. So, as per the partial fraction method, a divided by a linear factor, bs plus c divided by a quadratic factor, then multiplying the denominator. This is the as usual procedure to find ABC values here. So, once you get ABC values, you are substituted here, 7 into here 7s plus 13 is splitted into b, it is a divided by, it is bs plus c divided by, b value is minus 1 calculated, b value is minus 1 and c value is 3. So, in this way it is written. Now, while calculating the inverse, first term is simple here, 1 upon s inverse is 1 it is. So, see the second term minus s plus 3 divided by a quadratic factor. So, as per the completing square method, always you are able to write the complete square method for the quadratic term. So, how it is written, s square plus 4s plus 13 using the completing square method, s plus 2 whole square, here k value is 4 as per the formula, k value is 4, k by 2 means s plus 2 whole square plus k square by 4, k square means k equal to 2, that is 1. So, then 13 is written as 3 square. If you simplify, s square plus 4s plus 4 plus 9. So, the addition 4 plus 9 is 13. So, this is simplified to the completing square method. So, once we have the denominator s plus 2 whole square, numerator there is a s term here, you also make s plus 2 in the numerator. So, minus of s plus 2 plus you make the adjustment here, so that the simplification of this numerator and this numerator must be same. So, minus s minus 2 plus 5 is 3. So, it is simplified as s plus 2 because we need s plus 2 in the numerator because already s plus 2 in the denominator. So, that you can split into two terms, s plus 2 divided by s plus 2 whole square plus 3 square. The second constant term 5 divided by the same. So, the inverse finally 1 upon s is 1. This is by the shifting theorem. First shifting theorem one can write, compare with e raised to at into cos bt. So, a is minus 2 here. What is the Laplace transform of e raised to at into cos bt? It is s minus 2 divided by s minus 2 whole square plus b square. So, a is minus 2, b is 3. So, e raised to minus at into cos 3t, that is the inverse of this term. Similarly, this can be matched with the e raised to at into sin bt term. So, a is minus 2, for that b divided by, the main formula is b divided by s minus a whole square plus b square. So, 3 should be there in the numerator, that is why divided by 3 is taken. So, e raised to minus 2t sin 3t. So, in this way the partial fractions are used in finding the inverse. So, coming to another type of method, inverse Laplace transform using the Laplace transform of integrals. We know already the Laplace transform of integrals in the chapter Laplace transform. So, other teacher already taught about the Laplace transform of the integral functions. Integral is 0 to t f of t dt. Laplace transform of integral is equal to function of s divided by s, where f of s is, what is the function of s? This is the Laplace transform of f of t. F of s is the Laplace transform of the function of t. So, if you take L inverse on that side, the same formula we can write L inverse of function of s divided by s, taking L on the right hand side, L inverse is equal to the remaining 0 to t f of t dt. So, this is the inverse formula. L inverse of the function of s divided by s is equal to integrating from 0 to t f of t dt. What is f of t here? Where f of t is, it is known as L inverse of the function fs. You must know the inverse of function fs. So, the problems you can see, the problems of the type any function of s, its inverse is already known, then it is divided by s, you can use the Laplace transform of integral formula. Take for example L inverse of 1 divided by s into s minus 1. Here we can separate what is f of s, and s is already there. This can be written as L inverse of f of s divided by s. So, consider f of s is 1 upon s minus 1. So, we know the inverse of f of s here. We know the inverse of 1 divided by s minus 1. What is that? So, f of t is L inverse of f of s. F of t is L inverse of f of s. So, L inverse of 1 upon s minus 1, that is directly e raised to at type. 1 upon s minus a is e raised to at, a is 1, it is e raised to t. So, the Laplace transform of e raised to t is 1 upon s minus 1, then its inverse is e raised to at. So, we know we have identified f of s and then its inverse also known, substituting in the above formula. So, L inverse of f of s divided by s is equal to 0 to t f of t dt. That is L inverse of f of s is considered as 1 upon s minus 1 divided by s, it is there. So, integrating 0 to t f of t is calculated from the f of s, that is e raised to t dt. So, integrate e raised to t, that gives the inverse of the main problem. So, e raised to t is e raised to t, substitute the limits 0 to t. So, put t is equal to t and t is equal to 0 in the function e raised to t. So, t is equal to t is e raised to t minus t is equal to 0, e raised to 0, that is 1. So, finally, it is e raised to t minus 1, that is the inverse of 1 divided by s into s minus 1. So, one can use the partial fraction method also, the same problem. We already learnt about the partial fractions. You can see the denominators, there are linear and non-repeated factors. One can use the partial fraction method, 1 upon s into s minus 1, 1 upon s into s minus 1. So, by partial fraction method, a upon s, b upon s minus 1. So, the same problem, we have two methods are available. One can refer the partial fraction method, or using the integral Laplace transform of integral. Take the another example, it is 1 upon s cube plus 4s, 1 upon s cube plus 4x. Find the L inverse of 1 upon s cube plus 4s. So, one can write taking s common in the denominator, it is nothing but L inverse of 1 divided by s is common, s square plus 4s. Now, one can use the partial fraction method also again. See the denominator, one is a linear factor s, other one is quadratic factor. By partial fraction we can write a divided by s, then this is a quadratic term bs plus c divided by s square plus 4, it is 4 s square plus 4. Or we can use the inverse Laplace transform using the integral form. Here you identify the one function is f of s, the other one is divided by s. So, consider f of s is 1 divided by s square plus 1. So, we need to consider f of s whose inverse is known. If inverse of that f of s is not known, we do not consider that f s. So, f s I know the inverse of that. So, f of t is L inverse of f s, that is L inverse of 1 divided by s square plus 4. So, that is compared with the standard one, that is similar to the sin a t form. What is the Laplace transform of sin a t? So, a divided by s square plus a square. So, a is 2 here, I can write multiplying 2 and dividing 2. So, one can easily write 1 upon 2 into this is the standard one sin 2t. So, for this f of s, f of t is obtained. Now, using the formula L inverse of f of s divided by s is equal to the integration from 0 to t f of t dt. Therefore, L inverse of f of s we considered 1 divided by s square plus 4 divided by s, combining these two, that is the main problem, is equal to 0 to t, f of t is obtained already 1 upon 2 sin 2t dt. Now, integrating sin 2t, 1 upon 2 integration of sin 2t is minus cos 2t divided by 2, then apply the limits 0 to t. So, simplify this, 1 by 2 into 1 by 2, 1 by 4, minus sign you take outside, put the limits in place of t, t is equal to upper limit is t. So, that becomes same cos 2t, t equal to t, then t equal to lower limit 0, cos 0 is 1. So, minus 1. So, that is the inverse of the given problem. One can simplify removing the minus sign, it is 1 upon 4, 1 minus cos 2t. So, that is the inverse of 1 divided by s cube plus 4s. So, in that way we can solve the similar examples, 1 divided by s into s square minus 2, take f s is equal to 1 divided by s square minus 2 divided by s, and here divided by s square is there, means apply the same formula 2 times. First time you consider f s is equal to 1 upon s plus 2 divided by s, you will get the answer. Then you consider that as a f of t, and then f of s is equal to another problem 1 upon s plus 2 into divided by s. You apply the formula 2 times because of s square, these two examples 4 and 5 because of s square. Otherwise, there is always you can refer the partial fraction method. For third example, one is a linear factor and other one is quadratic. one can always use partial fractions a divided by s, bs plus c divided by this. And fourth example, it is repeated, linear repeated. S square means s is a linear factor repeated 2 times. For that, a divided by s, b divided by s square plus the another one is also linear, c divided by s plus 2. Then find out ABC values. Here s is a linear factor repeated, other one is quadratic. For that, a divided by s, b divided by s square, then cs plus d, this is a quadratic term, cs plus d divided by this, then find out ABCD values. So there is always two methods are available, whichever is convenient for you. You can refer either partial fraction method or fs divided by s method. Coming to the another important type examples, those examples involving trigonometric functions or logarithmic functions, we need to use another formula that you studied in Laplace transform. One of the formula is L you studied in already Laplace transform, L of t raised to n into f of t. F of t is multiplied by a polynomial t raised to n, that is equal to minus 1 raised to n, then differentiate n times the function fs. What is fs? Fs is the Laplace transform of f of t. So this in shortcut we can write minus 1 raised to n fn s. So fn s is nothing but fs is differentiated n times with respect to s. So this is the formula in Laplace transform. So I make it to inverse formula. Taking L on that side, one can write L inverse of fn s, that minus 1 raised to n is taken any one side, I taken other side, minus 1 raised to n t raised to n f of t. So this is the inverse transform of fns. Fns is the nth derivative of the function fs is equal to minus 1 raised to n t raised to n f of t. N may be any number, n equal to 1 it is first derivative, n equal to 2 second derivatives. The important is you can easily identify the problems, those inverse problems containing logarithmic terms or trigonometric functions, you directly apply this formula. So one example, evaluate L inverse of log s plus 1 upon s. So this is the example. Take f of s, whatever is given, that is f of s. F of s is the given function, that is logarithmic function, log of s plus 1 upon s. If you know the inverse of this, the problem gets over. So we don't know the inverse of logarithmic functions or trigonometric functions, so that I differentiate. Before differentiation, I can simplify using the logarithmic property. What is the logarithmic property? Log of a divided by b. One can write log a minus log b. So this is simplified to log of s plus 1 minus log of s. There is a property, log a by b is log a minus log b. Every stage you can check for the inverse tables are available or not. Log of s plus 1, we don't know the inverse of this, even log of s also. For that I can see by differentiating that. After the differentiation, the inverse formulas are available or not. Differentiating with respect to s. So I write fs differentiation is f dash s or f1 s. Log of s plus 1 differentiation is 1 divided by s plus 1. It is simple. Similarly, log s is 1 by s. So after the first derivative, you can check on the right hand side the inverse of these two terms available or not. If they are available, you stop the differentiation process. If they are not available, go for the second derivative. Then you check for the terms, their inverses are available or not. I know the inverse of 1 divided by s plus 1, I know the inverse of 1 divided by s. So, you stop the differentiation process at this derivative only. Now, you refer the main formula. So, I have differentiated once with respect to s here. So, putting n is equal to 1, use this formula. For n equal to 1, the main formula is reduced to f1s, that is f dash s, is equal to minus 1 raised to 1 t raised to 1 f of t. The main formula reduced to by putting n is equal to 1 here. So, substitute all the available functions. So, f dash s is known, substitute here, that is L inverse of 1 divided by s minus 1, 1 divided by s is equal to minus 1 into t f of t. So, f dash s is substituted here, and minus 1 raised to 1 is minus 1, t raised to 1 is t f of t. So, in this equation find out f of t, that is the inverse of the given problem. Or you write the inverse of this 1 upon s minus 1 inverse is e raised to t 1 upon s minus 1 minus what is the inverse of 1 by s, it is known 1 is equal to minus t into f of t. So, from this equation you can easily find f of t is equal to 1 minus e raised to t divided by t. So, that is the inverse of the given problem. The given problem is L inverse of log of s plus 1 divided by s. So, using this formula, in that it is obtained f of t value. So, like that, take another example, cot inverse of s by a. So, another example. Evaluate L inverse of cot inverse of s divided by a. So, whatever the function is given, L inverse of that, you consider f of s. Let f of s is equal to cot inverse of s by a. Now, you check for the inverse is available for this function or not. So, directly no, the inverse is not available, cot inverse or tan inverse. So, we go for differentiating this, differentiating with respect to s. So, f s becomes f dash of s. What is the derivative of cot inverse s by a? We know tan inverse of x derivative 1 divided by 1 plus x square, and what is the derivative of cot inverse x? That is minus 1 divided by 1 plus x square. So, like that, cot inverse derivative is 1 plus x is s by a whole square. So, minus 1 divided by 1 plus s by a whole square into s by a derivative, that is 1 by a. So, that completes the derivative of cot inverse s by a. Simplifying this, it is in the denominator s square plus a square comes in the numerator, finally it is a divided by s square plus a square. So, f dash s after the first derivative, it is minus a divided by s square plus a square. Now, at this moment you check for whether the inverse is available after the first derivative or not. So, this is matching with the standard form a divided by s square plus a square, its inverse is sin a t. So, you stop the differentiation, apply the formula by putting n is equal to 1. For n equal to 1 in the formula, that is L inverse of f dash s is equal to minus 1 raised to 1, that is minus 1 into t f of t. Substitute f dash s, it is there, L inverse of minus a divided by s square plus a square is equal to minus t into f of t. So, in this expression find out f of t. We know the L inverse of the left hand side, that is sin a t directly, or minus is a constant, it is sin a t, the right hand side is same, minus t, it is minus t into f of t. So, f of t is equal to sin a t divided by t, that is the inverse of the given problem. So, like that we have the examples, log of s square plus a square divided by s square plus b square, and log of 1 plus 1 divided by s square, and tan inverse of 2 by s square. We can easily recognize the problems. They are containing, fs is having either logarithmic terms or trigonometric terms. We can take another example here. Okay. Log of s square plus a square divided by s square plus b square. L inverse of log of s square plus a square upon s square plus b square. So, as it is, you consider fs is equal to that, fs is equal to log of s square plus a square divided by s square plus b square. So, at this moment we do not know the inverse of this logarithmic term. For that, I differentiate this f dash s. Before the differentiation, we simplify the logarithmic property. Log of a divided by b is a square plus a square minus log of a square plus b square. So, using the logarithmic property, it is written. Now, at this moment also I do not know the inverse of both the terms here. So, differentiating with respect to s, f dash s is equal to differentiation of log s square plus a square, that is 1 divided by s square plus a square into derivative of s square plus a square, that is 2s. Similarly, 1 divided by s square plus b square into derivative of that is 2s. So, after the first derivative, I can easily find the inverse of both the terms. They are matching with the cos a t terms. S divided by s square plus a square, it is the inverse of, it is the transform of cos a t. Similarly, s divided by s square plus b square, it is the inverse of, it is the transform of cos b t. Therefore, using n equal to 1 in the formula, f dash s is equal to minus 1 t raised to 1 f of t. Therefore, substituting f dash s, there are two terms, 2 into s divided by s square plus a square minus 2 into s divided by s square plus b square, right hand side minus t into f of t. So, I know the inverse of both the terms. 2 is common here, that implies 2 into, it is the standard one, cos a t minus 2 into, again this one is sin, cos b t is equal to minus t into f of t. Therefore, f of t is equal to, that is the inverse of the given problem. Dividing by 2, because of minus sign I am interchanging the terms here. 2 divided by t cos b t minus cos a t. So, that is the inverse transform of log of s square plus a square divided by log of s square plus b square. So, similarly you can try for the other examples. So, with this I conclude the today's session. So, next section we will go for the other formulas to calculate, that is convolution theorem and using the unit step function and their inverses in the next section. Thank you.